Hello and welcome back to this course, covering the exam topics for the JNCIS ENT certification. In this section of the course, we're reviewing Layer 2 security and loop prevention. In this lesson, we'll be demonstrating the configuration and monitoring of Rapid Spanning Tree Protocol. First, we'll review the diagram that represents the expected final state of our configuration. And then, before we jump into the live devices, we'll review the instructions for this lab. So, let's take a look at our diagram so we can discuss the key features we'll be illustrating. This diagram ought to look pretty familiar by now, as it's very similar to the last two lab demonstration diagrams we've had. On the bottom, we have switch 1, an SRX210, and on the top, we have switch 2, an SRX220. As before, the like-numbered interfaces on each switch are connected together. GE001 on switch 1 is connected to 1 on switch 2, 2 is connected to 2, 3 is connected to 3, and 5 is connected to 5. Switch 1 has two routing instances configured, VR11 and VR12. FE002 and FE003 are members of these respective interfaces. The interfaces FE002 and 3 are configured as routed interfaces, with the INET protocol family configured, and are each assigned an IPv4 address. A difference in this lab topology from the last is we now have a second trunk link configured between the two switches. Both interface 1 and 5 on switch 1 will be configured as trunks. Just like before, though, we have a couple VLAN interfaces configured, VLAN 11 and VLAN 12. We'll be using these interfaces to validate Layer 2 connectivity to the routing instances once our spanning tree topology is converged. Moving up to switch 2, we also have a similar configuration as before, with the exception of the additional trunk link between the two switches. Switch 2 will be configured with 2 access ports and 2 trunk ports. The 2 access ports are configured as members of separate VLANs. GE002 will be an access port for VLAN 11, and GE003 will be an access port for VLAN 12. As shown, this diagram poses a significant problem as we have a switching loop formed. With the 2 trunk links connected as alternate paths in the same broadcast domains. We'll configure RSTP and review the monitoring command outputs for RSTP to see how it resolves the loop. Now, let's review the instructions for this lab. First up, we'll take a look at the starting configuration of both of these switches. Then, starting on switch 2, we'll configure GE005 as a trunk port by copying the GE001 interface configuration to it, and we'll commit this configuration. On switch 1, we'll validate Layer 2 connectivity between the routing instances and the default instance by pinging between them. Once validated, we'll review and activate the RSTP and FE005 interface configurations and commit. At this point, we have a loop formed, as both port 1 and 5 on both switches are now active trunk links. However, we've configured Spanning Tree Protocol. On switch 2, we'll finish the Spanning Tree Protocol configuration and commit. Next, we'll review the bridge and interface information for the Spanning Tree Protocol instance on switch 2 to see how the topology has converged to avoid the switching loop, and review the details as to why it converged in the manner it did. Finally, to wrap up the configuration of RSTP, we'll ping from switch 1 again to the routing instances to validate Layer 2 connectivity. Now, a spanning tree lab demonstration wouldn't be complete without wreaking some havoc. So, the next steps will be to create a loop and then generate some broadcast frames to see what the effect is. On switch 2, we'll go ahead and delete the RSTP configuration we applied earlier and commit. Then, moving back over to switch 1 to have a good baseline, we'll review the current throughput statistics on the trunk links to see the number of packets per second being transmitted and received. Since there's no broadcast traffic yet, we expect this to be low. In order to generate some broadcast traffic, we'll clear the ARP table on switch 1 and then ping again between the default instance and one of the routing instances. We'll review the results of this ping and then review the throughput statistics on the trunk links once more to see how it's changed. So, let's go ahead and get started. First, we'll review the starting configuration on switch 1. We have minimal configuration once again, with the lab user configured, management services, and some default initial syslog configuration. Moving down to the interfaces, we see we have our management interface, GE000, and then our first trunk port, 001, which is a member of all VLANs. FE002 and 3 are both configured as routed interfaces, as these will be members of the routing instances later in the configuration. FE005 configuration is currently deactivated, though showing this will be our second trunk port and a member of all VLANs. We have the VLAN interface configuration for the interfaces in the default routing instance we will ping from. Moving further down, we see the default route for management and our RSTP configuration. It's currently deactivated, though we see that GE001 and FE005 will both be configured to participate in RSTP when the configuration is activated. Additionally, we've administratively set the bridge priority on switch 1, and we'll see how that affects RSTP a little later. Since we're on an SRX, we've set the mode to packet-based, and finally, we have the routing instances and VLANs configuration. FE002 is a member of VR11, and 3 is a member of VR12. Now, let's take a look at switch 2's configuration so we can get started updating the config. Similarly, switch 2 has minimal configuration with a user and management and other default configuration. When we move down to the interfaces, we have first our management interface, GE000, then we have the other interfaces. Only GE001, 2, and 3 are configured currently, with GE001 a trunk port and a member of V11 and V12 VLANs, and 2 and 3 are access ports and members of V11 and V12 respectively. Bringing up the remainder of the configuration, we see that we do have VLAN interfaces configured and attached to VLANs V11 and 12, though we won't be using these in this lab. So let's get started configuring our second trunk link. We'll enter configuration mode and copy the configuration from GE001 to GE005. Great. This has done what we're intending, of configuring GE005 as a trunk port and member of all VLANs. So let's commit this configuration and quit. Moving over to switch 1, let's ping between the default routing instance and the VR11 and VR12 instances to validate connectivity and that switch 2 is trunking and switching the VLANs appropriately. Great. Our pings are successful. Now let's activate our second trunk link and RSTP on switch 1. Recall, our RSTP configuration is present, though inactive, so we'll activate that. Also recall that our second trunks interface configuration is present, though inactive. We'll also activate this and commit. Great. Now let's just configure RSTP on switch 2 and see how the topology changes. We'll configure each port as point-to-point since they are directly connected to the other switch. Excellent. Now let's commit this configuration and see how we can check the topology. In this output, we see a lot of useful information. We have the bid of the bridge that this switch believes to be the root. This is clearly switch 1's bid since it has a priority value of 4096. Recall in switch 1's configuration that we manually specified the bridge priority to 4K or 4000. Further down the output, we have the root port on this bridge, which is GE001, then our configured timers for RSTP. Recall from other lessons that in RSTP, any switch can initiate a topology change. In this section of the output, we see the MAC address that the last topology change notification was received from. Finally, below, we see the local bridges bid, which has a default priority value set of 32,768. Now, let's take a look at the interface information for the interfaces participating in RSTP. We see here that we have 4 interfaces participating in RSTP. From the right, we have the role that each port has been assigned. Since we have 2 interfaces connected to the root bridge, one of them is a root port, and the other is assigned the alternate port role, and is in the blocking state. The alternate port role is an alternate root port that can be transitioned to a forwarding state if the root port becomes blocked for some reason. The reason this port became the alternate port, since the cost of both ports are equal, is due to the port ID. Since the top port has a lower port ID, it was assigned as the root port, and this one below the alternate port. Now, let's see how this spanning tree configuration translates into the Ethernet switching interface information. We see here that our 2 trunk ports are tagged traffic for both VLAN V11 and V12, and that the blocked alternate port shows that it is blocked by STP, and the other ports are unblocked. Finally, let's take a look at the detailed spanning tree interface information available. We see here that we have most of the same information available. The additional information, though, in this output from the above is the added link type information and below fields. Here, we see that this interface is configured as a point-to-point interface and is not an edge port. The designated bridge ID is the bid of the switch whose port is the designated port on this link. In this case, it is the root bridge. For GE002, however, we see that this interface is an edge port, and that the local port is the designated port, since the designated bridge ID is switch 2's bid. Now that we've seen how to configure Spanning Tree Protocol and monitor the Spanning Tree interface and instance information, let's have a little fun and see what happens when we're not running Spanning Tree Protocol appropriately and cause a loop. First, let's validate Layer 2 connectivity once more. Great. We're still able to ping the routing instances from the default instance on switch 1, since switch 2 is providing the layer 2 trunking and connectivity between the ports. Now, let's review the spanning tree configuration on switch 2 and generate some broadcast traffic to see what happens. Great. Now to illustrate what is about to happen, let's first take a look at the interface statistics of our two trunk ports. We see that we have had traffic traverse this link in the past, though currently the rate is 0 packets per second and 0 bits per second. Let's check the other trunk port. And the same thing here. We have a current throughput rate of 0 packets per second. Now, since switch 1 already has the ARP entries for the routing instance interfaces, we were pinging, let's clear the ARP table and then ping the remote interface. This will cause an ARP broadcast packet to be sent, and since we've misconfigured RSTP, we should see that we have a loop with a broadcast storm occurring. First, you'll notice that we do not receive any replies to our ping. When we cancel this ping, we see that we have 100% loss. This is likely due to there being a broadcast storm, which is overloading the interfaces or links and preventing the legitimate traffic from being forwarded. Let's take a look at the interface statistics again and see how things have changed. Wow, there's a lot more throughput now. We see that the current throughput rate is over 100,000 packets per second output, although we only see a bit over 1,000 per second input. Let's check the other trunk port. Here we have over 100,000 packets per second input. This indicates that the manner in which we created the storm, the packets are looping around in a single direction currently, leaving GE001 and coming back in FE005 on switch 1, forwarding around, and will continue to do so forever until the loop is broken or configuration is fixed. And this concludes the Spanning Tree Protocol lab demonstration. I appreciate you working through this with me. I hope that this lesson has been informative for you, and I would like to thank you for viewing.